Tonight, as you settle back and let the noise of the day fall away, there's something you should know about the place you're resting in. It feels familiar, steady, ordinary. But the space beneath your feet, the space you've lived inside your entire life, is anything but ordinary. Right now, without realizing it, you are sitting inside one of the largest cosmic voids ever discovered. A region so underdense, so improbable, that simulations suggest we shouldn't exist in a place like this at all. Astronomers didn't believe it when the first surveys appeared. When they mapped tens of thousands of galaxies around us, the pattern didn't match what the universe was supposed to look like. Too few galaxies, too much empty space, entire clusters simply missing. The numbers pointed to a quiet valley in the cosmic landscape nearly 2 billion light-years wide. A valley we are deep inside. And here's the part no one expected. Living in such a place doesn't just mean empty space around you. It means the universe looks different from your point of view. Gravity is weaker here. Space expands a little faster. Light drifts through this region with slightly less energy than it should. Even the measurements scientists use to calculate the age and size of the universe bend subtly around the emptiness surrounding you. If this enormous void truly wraps around the Milky Way, then some of the most important numbers in cosmology, numbers we've trusted for decades, may be skewed simply because of where we are standing in the universe. So tonight, as you drift with me through this quiet structure, you'll learn how it was found, why no one believed it, and what it means for everything you've ever been told about the cosmos. When you hear that you're sitting inside a cosmic underdensity, nearly 1 billion light-years wide, it sounds like something that should have been obvious long ago. Something we should have seen, measured, mapped. But the truth is far stranger. Astronomers almost missed it. And for a while, they didn't even believe their own data. The story begins in 2013, when 3 researchers, Keenan, Barger, and Cowie, set out to measure the distribution of galaxies around the Milky Way. They weren't searching for anything unusual. Their goal was simple: compare the density of nearby galaxies to the density farther away, and refine our understanding of how matter is arranged in the local universe. It was the kind of work that rarely produces surprises, until it suddenly does. They gathered data on roughly 35,000 galaxies, spanning hundreds of millions of light-years in every direction. They expected those galaxies to cluster around a fairly stable average density. That's the standard picture of cosmology. Local fluctuations here and there, but nothing too extreme. Nothing enormous. Nothing shocking. Instead, they found a deficit, not a small one. Not something that could be explained by noise or calibration. A 15 to 20% drop in the number of galaxies in the region surrounding the Milky Way. It wasn't that the galaxies were faint or hard to see. They simply weren't there. The local universe looked thinner, lighter, less populated than models predicted. At first, the team assumed something was wrong: a systematic error, a bias in the sample, a flaw in the instruments. Anything but the conclusion the data seemed to be pointing toward. As John Keenan later reflected, we kept thinking it was a calibration error until we realized it wasn't. So they checked their work again, and again, and again. Each time, the pattern returned. Fewer galaxies around us, gradually increasing to normal density only at much larger distances. The implication was unnerving. If the Milky Way sits in the middle of a region where matter is unusually scarce, then this region must be enormous, far larger than any void previously identified near our galaxy. A structure stretching nearly 1 billion light-years across. A structure large enough to influence large-scale measurements like the Hubble constant. A structure so big that it shouldn't exist by chance alone. Still, scientific skepticism demanded confirmation. So the group compared their findings with completely independent surveys, deeper infrared catalogs, wide-field optical surveys, redshift maps compiled by other teams around the world, different telescopes, different methods, different instruments. Same result. The void persisted across all datasets. It didn't fade. It didn't fragment. It didn't disappear when techniques changed. It was real, and it was enormous. And the strangest part wasn't its size. It was where we were standing. The Milky Way wasn't on the edge of the structure or passing through it. We were inside it, deep inside it. Imagine the moment that realization settled in. The universe around you is not uniform, not balanced, not the gentle cosmic average you were taught to picture. Instead, you occupy a valley carved into the large-scale fabric of existence, an unexpectedly quiet space between the brighter, denser ridges of the cosmic landscape. Not empty, but underfilled. A place where galaxies are fewer, gravity is softer, and the expansion of space behaves just a little differently than it does everywhere else. The transition from disbelief to acceptance happened slowly. The team tried every possible explanation that would avoid rewriting part of our cosmic neighborhood. Instrument error? No. Data selection? No. Statistical fluke? No. Miscalibration? No. Independent surveys? Yes, same results. Large-scale models? Yes, consistent. Void catalogs? Yes, the structure matched void-like behavior, but exceeded it in scale. And then came the moment they could no longer dismiss it. We might be inside a gigantic cosmic underdensity. That sentence, simple as it sounds, reshaped the way many cosmologists think about the local universe. Because if you are standing inside a region this large and this sparse, then what you see when you look outward is subtly altered. Distances shift, velocities stretch. Light behaves differently on its way to your telescope. Even your measurements of the universe's age and size can slide just a little without you noticing. For decades, cosmology assumed that the universe looks roughly the same everywhere on the largest scales. But discoveries like this one whisper a different possibility. Maybe our cosmic home is more unusual and more delicate than we once believed. But finding a void is one thing. Understanding what it does to the universe is another. When astronomers finally accepted that we might be living inside a vast underdensity, the next question rose almost immediately. What does that do to the way we measure the universe? Because if you are standing in an unusual place, the universe will not look quite the way it should. And strangely enough, that realization clicked into place at the exact moment cosmologists were wrestling with one of the most frustrating disagreements in modern astronomy. It began with two ways of measuring how fast the universe is expanding. The first comes from the cosmic microwave background, the relic radiation from when the universe was just 380,000 years old. The Planck satellite mapped that faint glow in extraordinary detail. From it, scientists derived an estimate for the universe's expansion rate, a number that fits beautifully within the standard model of cosmology. Smooth, predictable, mathematically elegant. The second method comes from the distance ladder. Supernovae, variable stars, and other standard candles that let us measure distances to galaxies in the nearby universe. These objects tell you how quickly galaxies are moving away from us right now, in the present-day cosmos. The problem? These two measurements don't agree. Not by a small margin, not by rounding errors, not by some tiny statistical quirk. The difference is nearly 9%, a gulf so large that scientists name the disagreement outright: the Hubble tension. If Planck is right, the universe is expanding at one speed. If supernova measurements are right, it is expanding significantly faster. And here's the strange part. Both measurements seem to be correct. Imagine hearing two clocks ticking at different speeds, but each clock is perfectly built, perfectly calibrated, perfectly consistent. Nothing is broken. Nothing is malfunctioning. You're just hearing two truths that refuse to line up. That is the Hubble tension. For a long time, cosmologists blamed the physics. Maybe dark energy was changing. Maybe there were new particles. Maybe gravity behaved differently on the largest scales. Theories multiplied. None stuck. None solved the discrepancy cleanly, without creating new contradictions. And then the idea emerged. What if it isn't the universe that's different? What if it's simply where we're standing inside it? Because living inside a large underdensity changes what you see. In a region where matter is scarce, gravity is weaker. Where gravity is weaker, space can expand a bit more freely. Where expansion is freer, galaxies drift away faster than they would in a region of normal density. And when you measure those galaxies using the distance ladder, the supernova approach, you'll naturally get a higher expansion rate. Not because the universe itself is expanding faster, but because your local neighborhood is. Picture a valley between mountains. Anywhere else, water flows gently downhill. But in the valley, water is pulled outward from all sides. If you stood in the middle, watching that water rush away, you might mistakenly conclude that the planet's gravity is stronger than it truly is. In reality, it is your location that is unusual, not the physics. The same happens with galaxies inside a void. They move outward more quickly because they are being pulled by the denser regions beyond the void's edge. So when supernova measurements tell us the universe is expanding faster than Planck suggests, it may not be a contradiction at all. It may simply reflect the fact that we are living in a place where galaxies have slightly higher outward velocities. That's why the void matters. It naturally explains the 9% mismatch. Supernova measurements look too high because they are watching galaxies accelerate out of a low-density region. Planck's measurement, on the other hand, looks at the early universe, long before voids existed. That measurement is unaffected by where we live today. It reflects the cosmic background, untouched by local structure. So the tension arises because we are comparing two very different vantage points: the universe as it was everywhere, and the universe as it looks specifically from inside a cosmic underdensity. When you realize that, the disagreement suddenly softens. It doesn't disappear entirely, but it shifts from an impossible contradiction to a natural expectation. As Dr. Lucas Lombreiser put it, the Hubble tension isn't a problem with cosmology. It may be a problem with where we live. That single sentence reframes the entire debate. Because if the Milky Way truly sits inside a billion light-year-wide void, then the numbers don't just begin to make sense. They begin to agree. The supernova method measures the expansion rate from inside a region where galaxies are being drawn outward faster than average. The cosmic microwave background measures the expansion rate from the early universe, when everything was uniform and free of the large-scale structures we see today. Combine these two facts, and the tension stops looking like a crisis and starts looking like a clue that we are in an unusual place, a clue that our measurements are subtly biased because of our surroundings, a clue that the universe isn't smooth the way we once assumed, and a clue that a vast void, quiet, enormous, surrounding us, has been shaping our understanding of the cosmos without us realizing it. For many scientists, this moment became a turning point. The Hubble tension, once a stubborn obstacle, became a lens through which the void suddenly made sense. The numbers didn't match because they weren't supposed to match. They were telling two halves of the same story. And if a void can bend something as fundamental as the expansion rate of the universe, then it must be understood more clearly, because its influence doesn't stop at galaxy motions. It touches gravity, light, structure formation, everything. To see why a void can have this effect, we need to understand what a void actually is. When you hear the word void, it's easy to imagine perfect emptiness, a hollow cavity in the universe where nothing at all exists. But that picture isn't quite right. A cosmic void is not empty space. It is simply less full than the rest of the universe. And the difference between empty and less full is far more important than it sounds. Inside a void, you still find matter, just not very much of it. There is dark matter drifting like a faint invisible mist. There is dark energy quietly pushing outward. There is thin, cold hydrogen gas spread out so sparsely that a cubic meter might hold just a handful of atoms. And here and there, a few lonely galaxies float across the quiet region, like faint lanterns in a vast, open plain. What makes a void special isn't the absence of matter, it's the weakness of gravity. Gravity shapes everything in the universe. It clumps dust into stars, stars into galaxies, galaxies into clusters. But in a void, there simply isn't enough matter for gravity to pull anything tightly together. It's like trying to make a snowball with only a few scattered flakes. The ingredients just aren't there. Because of that, the galaxies inside a void rarely grow into the giant spirals or massive clusters you see elsewhere. Instead, they remain small, dim, and fragile. Their motions are quiet. Their structure evolves slowly. They drift rather than gather. And where gravity is weak, something else steps forward: dark energy. Dark energy is the force that drives the expansion of the universe. Everywhere in space, it gently pushes outward. But in regions where matter is dense, gravity pushes back. In a void, there is no such resistance. There is no counterweight, no tension, no balancing act between forces. So dark energy wins easily, and the void expands faster than the universe around it. Astronomer Adam Rees once summarized it simply: dark energy dominates most strongly where matter is weakest. That single sentence describes exactly why voids behave the way they do. Think of a void as a low-gravity basin stretched across the cosmic landscape. In this basin, gravity doesn't gather matter inward the way it does in denser regions. Instead, matter slides outward, pulled toward the heavier structures ringing the void's edges. The basin gently deepens as time passes, and the low-density region slowly swells, expanding like a bubble forming inside a larger bubble. This image of a bubble inside a bubble is one of the easiest ways to visualize a void. The universe as a whole is expanding like a giant cosmic balloon. Inside that balloon, the voids are expanding even faster, inflating slightly ahead of the rest. They are bubbles within the bubble, growing at their own pace. And the larger the void, the more pronounced the effect. The KBC void surrounding us is so vast, so stretched across the cosmic fabric, that its expansion subtly shifts the way galaxies move across its interior. You can imagine space here relaxing a little more freely than usual, stretching with fewer obstacles, fewer anchors, fewer gravitational knots. In this environment, light travels differently as well, not faster or slower in the way science fiction imagines, but with less gravitational influence tugging on it. Photons glide through the void with a little less energy loss than they would in denser space. Subtle differences, gentle signatures, but measurable. The key is to understand that a void is not a place where physics stops. It's a place where physics tilts in favor of expansion, a place where the usual push-pull between gravity and dark energy is unbalanced, where dark energy breathes a little more deeply, and where matter obeys a different rhythm than it does in richer, heavier regions of the universe. Once you see a void this way, not as absence, but as imbalance, you start to understand why living inside one changes the way the universe looks from our perspective. And you begin to understand why the KBC void matters so much. It isn't just a hollow region. It's a region where the rules bend slightly, a calmer place, a lighter place, a place where gravity almost gives up. But seeing that from far away is different from living inside it. And the best way to grasp the consequences is to look at how physics behaves once you step deeper into this low-gravity basin. And inside such a place, physics begins to behave differently. The deeper you drift into a void, the more the familiar rules of the universe begin to tilt. Not break, not vanish, just soften, bend, and shift. And this is where the physics becomes truly surprising. Because in most of the universe, gravity is the sculptor. It gathers, it pulls, it shapes. But inside a void, something new happens, something that feels almost backward. Galaxies accelerate outward instead of inward. It sounds impossible at first. Everywhere else in the cosmos, galaxies are drawn together by gravity's quiet persistence. Clusters tighten, filaments pull, structures grow. But inside a void, inside a region where gravity is weak and matter is scarce, the opposite trend takes over. Galaxies slide outward, away from the center of the underdensity, drifting toward the denser walls that surround it. They don't fall inward. They are gently pushed outward, as if the void itself is exhaling. The Milky Way is part of that motion. Right now, your home galaxy is drifting at nearly 600,000 miles per hour, pulled partly by the dense Virgo cluster ahead of us and pushed partly by the emptiness behind us. This strange outward slide is evidence of the void's influence. We are not moving through a calm, balanced region of space. We are moving across a gradient in the cosmic fabric, drawn toward heavier matter and drifting away from lighter space. And it isn't just galaxies that behave differently here. Even light feels the difference. When a photon crosses a void, its energy changes slightly. This is called the integrated Sachs-Wolf effect. In denser regions, gravity steals a tiny bit of energy from light as it travels. Inside a void, there is less gravity to do so. As a photon enters the underdensity, gravity gives it a little boost. As it exits, gravity takes a little less than it normally would. The result is a subtle shift, tiny but measurable, imprinted on the light's temperature. You can see this effect in the cosmic microwave background. There are cold patches, slightly cooler regions, sitting in the same directions as enormous voids mapped by galaxy surveys. These patches aren't accidents. They're signatures of how weak gravity is inside underdense regions. They're markers showing that the void is not empty, but actively shaping the energy of ancient light as it passes through. This is the kind of physics that feels upside down. Inside most of the universe, gravity pulls you inward. Inside a void, the universe nudges you outward. Inside most of the universe, light loses energy. Inside a void, light loses less energy. Inside most of the universe, space expands steadily. Inside a void, space expands just a little faster. It's a world where the rules are the same, but the balance between them shifts. A world where gravity steps back and expansion steps forward. A world where dark energy enjoys the easiest battlefield it will ever find. As one researcher, Dr. Anna Pisani, put it, voids are the best laboratories for dark energy. That's true in every sense. Outside of voids, dark energy must compete with matter. It must thread its way between galaxies, between clusters, between thick strands of the cosmic web. But inside a void, there is almost nothing to push against it. And in that quiet environment, dark energy's influence becomes clearer, stronger, easier to detect. It reveals what expansion looks like when gravity loosens its grip. You could think of it like walking in deep water. When the water is thick around you, every movement is slow. But step into a place where the water becomes shallow and thin, and suddenly you can move freely again. In a void, the universe moves freely. Expansion glides effortlessly. Galaxies drift, carried by the gentle slope carved into the cosmic fabric. The KBC void surrounding us amplifies this effect on a breathtaking scale. It changes the flow of galaxies. It alters how we measure distances. It bends the behavior of light. It reshapes the background radiation that has traveled for more than 13 billion years. It makes physics feel unfamiliar, softened, expanded, inverted. For many astronomers, that inversion is the most striking part. A void isn't simply less dense, it's less gravitational. And that difference reshapes everything inside it. If you could observe the motions from far above, if you could somehow hover outside the underdensity, you would see galaxies gliding outward like dust moving across a shallow breeze. You would see light stretching differently. You would see the void breathing slowly, enlarging itself as the years pass. And if you zoomed out further still, you would begin to see a pattern, a structure surrounding the void, a shape that reveals why our region of the universe behaves this way. Because this strange physics isn't isolated, it's not random, and it's not unique to the KBC void. It is part of a larger architecture, a hidden framework that underlies the entire cosmos. To understand this strange space, we need to zoom out even further. The farther you pull back from the KBC void, the more the universe begins to reveal a hidden order, an architecture so vast and so intricate that it reshapes everything you thought you knew about how the cosmos is built. At human scales, space feels empty. At galactic scales, it feels scattered. But at truly cosmic scales, something extraordinary appears. A structure that connects everything, from the smallest dwarf galaxy to the largest clusters ever formed. This structure is called the cosmic web. It earned that name because of the way it stretches across the universe. Thin threads, dense knots, broad sheets, and cavernous gaps connecting into a pattern that resembles a three-dimensional web of luminous matter. If you could see it all at once, you'd be looking at a universe that resembles something like a Swiss cheese lattice, where the bright portions form a network of filaments and the dark portions, those vast empty cavities, are the voids in between. Most people imagine the universe as evenly filled with stars and galaxies, scattered more or less randomly. But the truth is stranger and far more beautiful. Matter doesn't spread evenly. Instead, it flows into long gravitational rivers, filaments that can stretch across hundreds of millions of light years. These filaments meet at bright nodes, where clusters of galaxies form. They create walls, broad, thin sheets of matter separating the immense cavities. And between those walls lie the voids, the enormous hollows where matter is scarce and expansion moves freely. Voids aren't the exception. They dominate. They make up nearly 90% of the universe's volume. 90%. Almost everything out there, on the largest scales, is nothing. That's one of the hardest truths for the human mind to accept. We picture the universe as full, bursting with galaxies and light. But take a step back, and the picture changes. The universe becomes a vast honeycomb of emptiness, with thin, bright lines tracing its structure. Galaxies form only along those lines, like beads threaded on invisible strings. We discovered this architecture not through imagination, but through data. Massive surveys that mapped millions of galaxies. The Sloan Digital Sky Survey, using redshift to measure distance, revealed the first clear picture of this network. When astronomers plotted the positions of galaxies in 3 dimensions, the pattern emerged unmistakably. Filaments, sheets, clusters, and voids forming a cosmic web unlike anything ever predicted by simple models. This was one of the most important moments in modern astronomy. It showed that the universe is not a smooth sea of galaxies. It's a landscape. Picture it. Filaments, narrow rivers of galaxies, each filled with dark matter scaffolding. Walls, enormous continental plates of galaxies stretching across the cosmos. Nodes, gravitational cities where hundreds or thousands of galaxies gather. Clusters, the brightest, heaviest islands of matter. Voids, the quiet oceans between these structures, expanding faster and pulling matter outward. This is the true shape of everything. This is the stage on which the universe performs. And you, your galaxy, your star, your planet, are a speck inside one tiny thread of this giant web. When you look up at the night sky, you're not seeing the whole story. You're seeing the lights inside a single room of a sprawling cosmic mansion. The Milky Way isn't at the center of anything. It isn't even perched on a major filament. It sits on the outskirts of a thread within an enormous underdensity. In the context of the cosmic web, our home galaxy is not a dominant presence. It's a grain of dust floating on one faint strand of the universe's skeleton. Dr. J. Richard Bond once said, "The cosmic web is the universe's true skeleton." He meant it literally. Dark matter forms the bones. Galaxies fill the flesh. Voids shape the empty spaces between. The web holds everything together, not as fixed structure, but as a dynamic, evolving pattern formed over billions of years. When you understand this architecture, the KBC void becomes easier to visualize. It's not a strange anomaly or a hole punched into the cosmos. It's one of the enormous cavities that naturally arise between filaments and walls, a basin between the ridges, a valley between the mountains. But scale matters. The KBC void isn't just any valley. It's one of the deepest and broadest ever mapped near the Milky Way. Its edges touch major filaments. Its interior is underdense across huge distances. It sits inside the web like a hollow chamber, surrounded by bright, dense structures on all sides. Knowing this changes how you imagine the universe. It no longer feels random. It feels designed, not by intent, but by the quiet interactions of gravity, matter, and expansion over unimaginable time. The web isn't just the structure of the universe. It's the reason the universe behaves the way it does. And standing inside this web, inside one of its largest cavities, gives you a unique vantage point, a tilted perspective, a slightly distorted lens through which you view everything else. Understanding that perspective brings you closer to grasping the true nature of our cosmic home. Because before you can appreciate what the void does to your measurements of the universe, you must understand where exactly you are in this architecture. So where are we on this cosmic map? When you picture the KBC void, it's easy to imagine the Milky Way floating calmly at its center, like a tiny boat drifting in the still heart of a cosmic lake. But that isn't quite where we are. The truth is a little more complicated, and somehow even more intriguing. The Milky Way is not at the center of the void, but it sits deep inside it, close enough that everything we measure, everything we observe, every number we trust about the universe is influenced by where we stand. Our galaxy lies roughly 200 to 400 million light years from the void's center. In cosmic terms, that's both far and incredibly close. Far enough that we're not perched at the lowest point of this underdense valley, but close enough that we're definitely in the basin. We are not skirting the edges or drifting along the rim. We are embedded in the quiet, thinned-out interior of this massive structure. And that matters, because even though we aren't right at the center, we are well within the region where gravity becomes noticeably weaker and expansion becomes noticeably stronger. This is the zone where galaxies accelerate outward. This is where distances shift. This is where the cosmic microwave background feels the difference. This is where supernova measurements take on a bias. Being 2 to 400 million light years off-center doesn't save us from the void's influence. It places us squarely in the region where that influence is most noticeable. Think of it like living inside a valley carved into a vast mountain range. You don't need to stand at the deepest point to feel the slope beneath your feet. As long as you are in the valley, the ground still tilts. The horizon still changes. Your perception still shifts. Gravity still guides you outward. Whether you're in the middle or off to the side, the valley defines your view. That's exactly what the universe is doing to us. If the Milky Way were sitting on one of the bright filaments, those dense, massive strands of the cosmic web, our observations would look different. Very different. Filaments are the opposite of voids. They are places where gravity is strong, where clusters form, where galaxies gather and grow. Had we lived on such a filament, our measurements of the universe's expansion would be pulled downward, not upward. Distances would appear slightly compressed, not stretched. Light passing through our region would lose more energy, not less. The Hubble tension might never have existed at all. Cosmology textbooks might have taken a different shape. In other words, if Earth had been born in a different neighborhood, the universe would look different to us. That's one of the most personal truths in all of cosmology. Not philosophical, not symbolic, literal. Where you live in the universe alters what you see when you study it. Your home galaxy is not simply a point of observation. It is part of the equation. This is where the idea becomes intimate. Everything you've learned about cosmology, distances, expansion, structure, age, has been measured from inside a quiet, low-density valley. That valley is shaping your perception. It is bending the numbers. It is guiding the motion of the Milky Way and everything around it. This is not the neutral vantage point we once assumed it was. It is a tilted frame, a gentle slope, a quiet chamber where the universe behaves differently. And somehow, this makes the cosmos feel more personal, not less. You live in a unique place. Your galaxy drifts through a rare kind of landscape. The night sky you see is painted by the environment surrounding you. Not wrong, not broken, just shaped by the valley it inhabits. But the strangest part is what surrounds us. If you step back even farther from the Milky Way, farther than the KBC void, farther than the quiet basin we live inside, you encounter one of the most astonishing structures in the known universe. It's vast, it's intricate, and it holds our galaxy, our neighbors, and tens of thousands of others in a slow, graceful flow. This structure is called Laniakea, meaning immense heaven, and its immensity is no exaggeration. Laniakea contains roughly 100,000 galaxies, 100,000 island universes, each bursting with stars, planets, nebulae, and worlds we may never see. All of them are part of a single gravitational continent, a supercluster so large that even light would take hundreds of millions of years to cross its full width. But here's the part that bends the mind. Laniakea, this enormous supercluster, sits inside a region of space that is surprisingly underdense. A supercluster inside a void. That sounds impossible at first. Overwhelming structures are supposed to grow in dense environments, where galaxies gather, where dark matter pools, where gravity has been sculpting the landscape for billions of years. But Laniakea didn't form in the middle of a heavy, crowded region. Instead, it is perched inside a quieter, thinner part of the cosmic web. This is one of the great puzzles of our cosmic neighborhood, a paradox of scale. Laniakea is enormous in size, but its surroundings are light. It is massive in extent, but not in density. It is structurally grand, but gravitationally gentle. large, but not thick. To make sense of this, you need to imagine Laniakea not as a mountain rising from the cosmic landscape, but as a broad, sprawling plain. A region defined not by extreme gravitational strength, but by the flow of galaxies, all moving together toward a mysterious focal point. That focal point is known as the Great Attractor. The Great Attractor isn't a single object. It's not a star, or a black hole, or a cluster. It's a region of intense gravitational influence buried deep inside the supercluster. A gravitational basin pulling galaxies across immense distances. The Milky Way is part of that flow. So are the galaxies of the Virgo cluster, the Centaurus cluster, the Pavo-Indus filament, and many others. Together, they drift as if sliding down a vast invisible slope carved into the fabric of space. This flow is what defines Laniakea. Not density, not concentration, but motion. 100,000 galaxies, all following the same slow river of gravity toward the same distant anchor point. And yet, the paradox remains. How can such a grand structure exist inside a region that is, on average, underdense? The answer lies in the nature of the cosmic web. Voids do not mean total emptiness. They mean less matter, not none. The universe forms structure along filaments and walls that wrap around voids, like the boundaries of immense bubbles. Laniakea sits along the edge of one of these deep underdense regions, flowing along a gentle ridge inside a larger, sparse basin. There is enough matter to form a supercluster, but not enough to erase the underdensity. Enough to shape a gravitational continent, but not enough to turn the region into a dense metropolitan core like the Coma supercluster or the Shapley concentration. This is why Laniakea doesn't break the definition of the void. It fits inside it, an elegant part of the terrain, not an exception to it. A stretch of land rising slightly from a valley floor, but still very much within the valley. You can imagine it as standing in a vast desert. Even a large hill does not make the desert go away. The hill is part of the desert. The emptiness is still all around it. In the same way, Laniakea is a hill, grand, sprawling, majestic, but still resting inside a region that is fundamentally thin and quiet on the largest scales. This perspective helps explain why the Milky Way experiences the motions it does. We are attached to a supercluster. We are part of its flow. Yet we are also embedded in a void-expanding environment. Gravity from the Great Attractor pulls us one way. The emptiness behind us pushes us another. These competing influences shape the motion of our galaxy, our drift through space, and affect the way we measure the universe around us. The strangest part of all is that Laniakea, despite its immense size, cannot overpower the underdensity that surrounds it. The void's influence still wins on the largest scales. The emptiness is too vast. The gravitational basin is too deep. Even 100,000 galaxies cannot fill in a valley carved across 1 billion light years. Understanding this brings a new appreciation for the subtlety of our cosmic home. Large does not always mean dense. Grand does not always mean heavy. And a supercluster does not always live in a crowded neighborhood. We live in a universe full of patterns that defy our instincts. Patterns where lightness shapes motion, where emptiness guides structure, where the largest things grow in the quietest places. And our galaxy is still on the move. Even though the KBC void is the vast underdensity shaping much of our large-scale perspective, it isn't the only emptiness near us. There is another hollow region, much smaller, much closer, which has been quietly influencing the Milky Way's motion for millions of years. It's called the local void, and although it is nowhere near the size of the KBC basin, its proximity makes it surprisingly powerful. If the KBC void is a massive valley carved into the landscape of the cosmic web, then the local void is like a smaller depression sitting right beside the ridge where the Milky Way lives. Our galaxy sits along the boundary, close enough to feel its pull, or rather, its lack of pull, because voids influence galaxies not by attracting them, but by failing to. The local void is emptier than average, with too little matter to provide any meaningful gravitational tug. So the galaxies bordering it, including our own, naturally flow away from it. They drift toward regions where matter is denser, regions where gravity does have something to say. On the opposite side of the Milky Way from the local void lies the Virgo cluster, a massive gravitational hub containing more than 1,000 galaxies. Virgo pulls us in. The local void pushes us out. This combination, push from the emptiness, pull from the cluster, creates a motion that is both steady and measurable. It shapes the peculiar velocity of the Milky Way, the motion of our galaxy relative to the cosmic expansion. That motion is fast, very fast. Right now, the Milky Way is moving through space at roughly 627 kilometers per second, or almost 1.4 million miles per hour, relative to the cosmic microwave background. This extraordinary speed is not caused by the universe's expansion itself. It is caused by the uneven distribution of matter surrounding us. Gravity from Virgo tugs us forward. Gravity from the filament we occupy guides us sideways. The emptiness of the local void allows us to slide outward more easily. You can picture it as a galaxy caught in a cosmic crosswind. If the local void were filled with more matter, its gravitational anchor would hold us more tightly in place. We would drift more slowly. Our peculiar velocity would be smaller. Instead, the local void's emptiness gives us freedom of motion. It removes friction from our part of the universe, letting us slide across the cosmic landscape with fewer constraints. This is one of the most important clues that voids truly matter. They shape the motions of galaxies. They influence the structure of clusters. They alter how matter flows across the web. They participate in the choreography of the universe. For decades, astronomers believed that the Virgo cluster alone was responsible for our motion. But deeper surveys showed the truth was more nuanced. The push from the local void was just as important as the pull from Virgo. Without both forces, the path of the Milky Way across space would look very different. We might not be moving as quickly. We might not be moving in the same direction. We might not be part of the same gravitational flow at all. This dual influence, push from emptiness, pull from structure, reveals a deeper truth about the cosmic web. What's missing can be as powerful as what's present. You don't need a massive galaxy cluster to move a galaxy. Sometimes, all you need is a void nearby, an absence that removes resistance, a silence that changes the tempo. In this way, voids become quiet sculptors of cosmic motion, guiding galaxies not with gravity's hand, but with gravity's absence. And this isn't just theory or metaphor. The motion of the Milky Way has been mapped with exquisite precision using the cosmic microwave background. The hot and cold dipole pattern imprinted on the CMB is a direct record of our galaxy's movement through space. It shows our direction. It shows our speed. It shows the peculiar velocity created by the local void and the Virgo cluster together. Every galaxy near a void behaves the same way. They slide outward toward the denser walls of the cosmic web. This consistent pattern is one of the strongest proofs that voids affect us, not just by expanding faster, not just by distorting measurements, but by literally moving galaxies through space. One of the quiet ironies of cosmology is that emptiness has agency. It shapes, it directs, it accelerates. And our galaxy is a perfect example of that strange truth. We are part of Laniakia's flow, shaped by the Great Attractor. We are part of the KBC void, shaped by its weak gravity. We are part of the local void's boundary, pushed gently outward. And all of these motions weave together to create the path we follow across the universe. But these voids don't only move galaxies. Their influence runs deeper, touches more subtle aspects of the cosmos. They reach out and shape something even more delicate than motion, something ancient and universal, something woven into the background of the universe itself. Because voids don't just move galaxies, they trick the light itself. When you think about the influence of a void, it's easy to picture galaxies drifting, sliding, flowing across space as gravity weakens and expansion takes over. But the strangest effects aren't on the galaxies. They're on the light itself, the ancient radiation that crosses these vast underdense regions on its way to our telescopes. Light, in almost every part of the universe, loses a tiny bit of energy as it travels through gravitational fields. This is normal. Gravity gently pulls on photons, stretching their wavelengths, draining just the smallest fraction of their energy. It's one of the quiet rules of the cosmos. But inside a void, that rule changes. In a region where gravity is unusually weak, light doesn't lose as much energy as it normally would. Sometimes, depending on the path it takes, it even gains a tiny boost. The shift is minuscule, far too small for your eyes to notice, but it's big enough for precision instruments to detect. It's big enough to leave fingerprints on the universe's oldest light. This delicate interaction is known as the integrated Sachs-Wolf effect, or ISW for short. Imagine a photon entering a void. In a dense region, the gravitational well is deep. The photon falls in, climbs out, and leaves with slightly less energy. But in a void, the well is shallow. The photon still falls in, but when it climbs out, gravity has changed just enough during its journey, because the void is expanding, that the photon can sometimes escape with a little more energy than it started with. It's a strange, counterintuitive effect. Gravity and expansion briefly tug in different directions, and the photon ends up with a different energy than it should have. You can see the effects of this on the cosmic microwave background, the faint afterglow of the Big Bang. The CMB isn't perfectly uniform. It has tiny temperature variations, ripples only millionths of a degree apart. And when astronomers map those variations onto the locations of known voids, a pattern emerges. Where there are voids, the CMB tends to look slightly cooler. Not dramatically, not glaringly, but consistently. These cool spots, these slight temperature dips, match the locations of some of the largest voids ever found. It's as if each void leaves a subtle shadow on the CMB, a tiny lowering of temperature caused by the ISW effect, a whisper of how light has been nudged and shifted as it passed through a region with weaker gravity and greater expansion. This is one of the most delicate measurements in cosmology. Detecting the ISW effect requires combining massive galaxy surveys with deep, high-resolution maps of the CMB. But the evidence is growing. Independent surveys, Sloan Digital Sky Survey, 2MASS, WISE, DES, and others, have each confirmed the same thing. Voids do not just shape galaxies. They shape the universe's oldest radiation. And when you layer all this information together, galaxy surveys, void catalogs, CMB maps, gravitational lensing studies, you begin to see how voids create a different kind of cosmic lens. Not the strong gravitational lensing that bends starlight into arcs around massive clusters, but a softer, quieter lensing that subtly changes the brightness and temperature of photons traveling through thin space. In dense regions, gravitational lensing magnifies and distorts. In voids, the lensing is reversed. Light spreads out more. It loses less energy. It arrives with a slightly different temperature than expected. It's another quiet inversion of the usual cosmic rules. Another reminder that voids aren't empty. They're just unusual, tilted pockets of the universe where the familiar balance between gravity and expansion tips in favor of emptiness. When astronomers first started seeing CMB anomalies aligned with known voids, the reaction was the same one that followed the discovery of the KBC void: disbelief. It seemed too subtle, too fragile a signal to detect reliably. But the more surveys piled in, the clearer the pattern became. Voids shift the paths of photons. Voids alter the energy of ancient light. Voids carve faint shadows across the background of the universe. And once again, the place where we live, our own underdense environment, plays a part in what we see when we look outward. The CMB we measure is slightly shaped by the void surrounding us. The light that reaches us carries just a hint of that influence. All of this leads to an even larger realization, one that has become one of the deepest problems in modern cosmology. If voids change the way galaxies move, if they shift the energy of photons, if they affect the temperature of the CMB, then what else might they be distorting? What else might look wrong simply because of where we are? And this leads to one of cosmology's biggest crises. By the time astronomers recognized that voids could change the motion of galaxies and shift the energy of ancient light, a deeper realization had begun to take shape, one that touched the very foundation of modern cosmology. Because if living inside a void tilts the way we see the universe, then some of our most trusted measurements may not be telling us the whole story. And nowhere is this more obvious than in the problem known as the Hubble tension. The Hubble tension is one of the greatest puzzles in astrophysics today. It's a disagreement between two ways of measuring how fast the universe is expanding. One method, based on the cosmic microwave background, suggests a slower, older, more gradual expansion. The other, based on nearby supernovae, suggests a faster, more recent expansion. The numbers differ by almost 9%, a gap so large and so persistent that it can't be explained by small errors or chance. If the faster expansion rate is correct, then the universe must be younger than we think. A lot younger. The official age of the universe, based on the cosmic microwave background, is about 13.8 billion years. But if expansion has been happening more quickly than expected, that number shrinks. In some models, it shrinks enough to create a troubling paradox. Certain stars would appear older than the universe containing them. That's not a poetic exaggeration. It's a literal implication. We have stars in the Milky Way, ancient red giants, metal-poor relics of the early cosmos, whose estimated ages push extremely close to the edge of the universe's official age. In a younger universe, those stars become impossible. They would have formed before the universe existed. And if nature gives you a paradox that extreme, something in your model has to give. For years, cosmologists tried to explain the Hubble tension by modifying the physics of the early universe. They proposed new kinds of dark energy, new particles, early bursts of expansion, shifts in primordial density fluctuations, anything that might reconcile the two disagreeing measurements. But none of the explanations were simple, none were elegant, and none fit the data without creating new problems elsewhere. Then came the possibility everyone had overlooked. Maybe the universe itself is not broken. Maybe the measurements are not wrong. Maybe the contradiction is simply a trick of perspective. Maybe the problem is where we live. If the Milky Way sits inside a massive underdensity, like the KBC void, then galaxies around us would appear to be moving away faster than they should. This would naturally inflate the expansion rate measured using supernovae. It would make the universe appear to be expanding more quickly in our local region, even if the global expansion rate is slower and fully consistent with the cosmic microwave background. This single idea cleans up the contradiction without requiring new physics. It preserves the universe's age. It preserves the integrity of the cosmic microwave background. It preserves the ages of ancient stars. And it fits the simplest rule in science. The simplest explanation is often the correct one. A void around us, one that is less dense, expanding slightly faster, and large enough to matter, creates exactly the kind of upward bias needed to produce the Hubble tension. It doesn't eliminate the disagreement entirely, but it reduces it dramatically. It brings the two numbers closer together, softening the paradox and shifting the burden away from exotic physics and toward geography. In this view, the universe isn't younger than we thought. We're just standing in a place that makes it look younger. It's a humbling idea. It means we cannot simply assume we occupy a neutral vantage point. It means the cosmos is not a smooth, uniform stage. It means the landscape isn't flat. We're in a valley, one that stretches for billions of light years, and everything we measure is filtered through the shape of that valley. For many astronomers, this interpretation feels surprisingly natural. It connects the Hubble tension with the structure of the cosmic web. It links the motion of galaxies with the distortions of ancient light. It turns a crisis in cosmology into a clue that our region of the universe is more unusual than we realized. It doesn't settle the debate forever, but it changes its tone. Instead of asking, "What is broken in cosmology?" scientists now ask, "What is special about where we live?" And that question cuts to the heart of a much deeper issue, one that stretches beyond equations, beyond surveys, beyond the physics of voids themselves. And this raises a philosophical question. For most of scientific history, one idea has guided the way we think about the universe: the belief that we do not occupy a special place. This is the Copernican principle, the quiet philosophical backbone of modern cosmology. It tells us that Earth isn't central. The sun isn't central. The Milky Way isn't central. And nothing about our position in the cosmos is unique. We are ordinary observers in an ordinary location, looking out at an ordinary universe. But the discovery that we may be living inside a massive, deep underdensity, a region so large and so improbable that its existence challenges statistical expectations, forces us to revisit that old assumption. Because if the KBC void is real, and if the Milky Way sits deep inside it, then our position might not be ordinary at all. In fact, some analyses suggest that living in a void this large is equivalent to occupying a 10 sigma anomaly. In the language of statistics, that means almost impossible, not just unlikely, not just rare. A 10 sigma deviation is something that shouldn't happen through random chance in the entire history of the observable universe. And yet, here we are. This doesn't necessarily break the Copernican principle, but it does challenge it. The principle isn't a rule of physics. It's a guiding assumption, a way of telling ourselves that the universe has no preferred vantage point. But assumptions can be tested, they can be bent, and every so often they can be revised. If we are living inside a 10 sigma underdensity, then the universe may not be as uniform as we imagined. It may have deeper variations, bigger swings in density, larger stretches of emptiness than the standard models predict. The cosmic web may be rougher, more uneven, more textured than our equations assume. The idea that matter smooths out on the largest scales may not be entirely true. And if it isn't, then the way we interpret observations must change as well. This raises an unsettling but fascinating possibility. Maybe the universe isn't uniform after all. Maybe the cosmic landscape is patchy. Maybe some regions expand faster. Maybe some regions hold deep basins where galaxies move differently. Maybe some areas are richer, denser, louder. Maybe others, like the place we inhabit, are quieter, thinner, and more influenced by dark energy. In this view, our home isn't special because it was chosen. It's special because the universe has texture. It has a topology shaped by ancient fluctuations, long before stars, long before galaxies, long before the cosmic web took its familiar form. If those early ripples were strong enough in certain places, they could grow into vast underdensities like the KBC void. Rare, yes, but not impossible. This perspective reframes the entire question. It's not why us. It's why is the universe shaped this way? Because if enormous voids are part of the natural structure of the cosmos, then living inside one does not violate the Copernican principle. It simply means we finally realize something that was true all along. The universe has wild variations, and we happen to sit inside one. But if, on the other hand, the void is too large, too deep, too improbable to arise naturally, then we are forced to consider another possibility. Perhaps we do inhabit a special location after all, not in a mystical sense, not in a teleological sense, but in a structural sense, like living near a rare geological formation on Earth. It wouldn't make you chosen. It would simply make your surroundings unusual. And unusual surroundings can change what you see. They can shape how you measure cosmic expansion. They can tilt your interpretation of the cosmic microwave background. They can affect the perceived ages of the oldest stars. They can feed directly into the Hubble tension and other cosmic puzzles. Whether this violates the Copernican worldview depends on how improbable the void truly is. And to answer that, to understand whether the cosmic structure around us is a random fluctuation or an ancient imprint, we have to go back to the very beginning, to a time before galaxies, before atoms, before even the first particles fused. Everything we see today, the voids, the filaments, the superclusters, was seeded in the universe's earliest moments. To answer that, we have to go back to the beginning. To understand how a vast underdensity like the KBC void can exist, you have to travel back to the earliest moments of the universe, far earlier than the first stars, the first galaxies, or even the first atoms. You have to return to the instant when the universe was a fraction of a second old, when its size was smaller than a grain of dust, and when everything we see today was being imprinted into existence. That moment is known as inflation. Inflation wasn't just expansion. It was runaway expansion. Space stretching faster than the speed of light, doubling again and again in an unimaginably short amount of time. In that brief window, the universe grew from subatomic to cosmic in size, smoothing out irregularities and flattening the fabric of space-time. It was supposed to make the universe uniform, even, predictable. But inflation did something else too, something subtle and profoundly important. It amplified the smallest quantum fluctuations, tiny ripples in energy, appearing and vanishing faster than any instrument could detect, stretching them across cosmic scales. These fluctuations became the seeds of everything: the galaxies, the clusters, the filaments, and the voids. Imagine quantum foam, bubbles of slightly higher and slightly lower density, popping in and out of existence at the smallest scales. During inflation, these bubbles were pulled apart and frozen into place. Regions where energy density was a little higher would later collapse into galaxies and clusters. Regions where it was a little lower would eventually grow into voids. This is the origin of the cosmic web. Tiny differences, far smaller than fluctuations on the surface of the sun, were stretched until they spanned light years, then millions of light years, then billions. By the time inflation ended, the blueprint of the entire cosmic structure was already etched into the universe. The rest was just gravity and time. And the evidence for this is still visible today. When astronomers look at the cosmic microwave background, they see faint temperature variations, cool patches, and warm patches, only millionths of a degree apart. These variations are the direct signatures of those early fluctuations. They are snapshots of the baby universe, frozen in place like ancient fossils. The seeds of the modern universe lie in those tiny ripples. Some of those early low-density patches grew over time, stretching as gravity pulled matter away from them and toward denser regions nearby. Over billions of years, these patches expanded, deepened, and evolved into the enormous voids we see today. They became the cavernous hollows between the filaments of the cosmic web, and one of those early low-density patches eventually became our own cosmic home. The KBC void is not a hole punched into the universe. It is the natural descendant of a small fluctuation seeded during the earliest moments of inflation, a region that started just slightly below average density, then expanded and thinned as gravity sculpted the surrounding space. Over time, that slight dip became a broad basin, one that now spans nearly 2 billion light-years. Our void is simply an overgrown, low-density patch, a delicate relic of quantum physics written on the largest possible canvas. This perspective softens the paradox of living in such a rare environment. It doesn't eliminate the questions. How deep should it be? How wide? How improbable? But it places them in context. The universe is full of ancient imprints from inflation, and some of them grow into structures far larger and stranger than our intuition expects. Voids, in this sense, are not mistakes. They are memories, echoes of fluctuations born before time had meaning, stretched across the fabric of the universe by an event we still do not fully understand. And once you see voids this way, the KBC underdensity becomes something more beautiful than empty space. It becomes a cosmic ancestry, a signature of the earliest moments of creation, a quiet valley whose existence was decided long before galaxies ever formed. It also brings us back to the present, back to the quiet place where you're sitting tonight, drifting through a universe shaped by events so ancient that even light remembers them. And now, let's return to where we are tonight. Tonight, after wandering across billions of light years, after tracing the slow drift of galaxies and the soft pull of gravity, you can finally let the scale of it all settle around you. Because for all its strangeness, for all its vastness, the place you live in is not chaotic or threatening. It is quiet. It is gentle. It is calm. The void surrounding you, the enormous underdensity stretching across the cosmic web, is not an abyss. It is a cradle, a quiet pocket of the universe where gravity softens, where expansion smooths the edges of motion, where galaxies drift with a slow, serene momentum. It is a place shaped by ancient physics, but experienced by you as stillness. You don't need to solve the universe tonight. You don't need to untangle the tension between different measurements, or trace the paths of galaxies, or map the boundaries of dark matter. You don't need to hold the equations of cosmology in your mind. All of that can wait for the daylight hours if you want it to. For now, you can simply rest in the knowledge that the cosmos you inhabit is not rushing or roaring. It is expanding gently, carrying you with it in a motion older than the stars. Look at the Milky Way, not as a mystery to solve, but as a companion drifting through this quiet valley. Your galaxy glides across space at hundreds of kilometers per second. Yet from where you sit, it feels motionless. It feels steady. It feels like home. The void doesn't disturb that motion. It softens it. It turns the surrounding universe into a vast, slow tide, carrying you forward without urgency or noise. The expansion of the universe, too, is gentle here. In a dense cluster, gravity claws at space, fighting the outward push. But in this underdense region, expansion flows more freely, not violently, not explosively, just a quiet stretching of space, like a deep breath drawn over billions of years. It is the universe resetting itself, moment by moment, in a rhythm that asks nothing of you. There is comfort in knowing this, comfort in recognizing that your place in the cosmos is calm, comfort in realizing that among all the possible environments the universe could have given you, it offered you this one, a peaceful corner of an immense and ancient structure. In the words of one astronomer, In the vastness of all that exists, our small place is a quiet one. You don't have to do anything with that knowledge. You can simply let it surround you. Let it soften your breathing. Let it ease whatever thoughts are still lingering from the day. Let it remind you how gentle the universe can be. Because the void is not something to fear. It is a soft, expansive silence, a cosmic lullaby. And tonight, as your mind drifts, you drift with it, carried by the slow motion of a galaxy moving through a quiet place in a quiet universe on a quiet night. You are safe here. You are small in the most comforting way. And the cosmos, vast, ancient, and unfolding, continues on around you, patient and unhurried. Good night.